Okay, let us solve this example using Bernoulli's equation. Okay, it says, excuse me, water flows at a speed of 5.7 meters per second through a horizontal pipe of diameter 3.4 centimeters. The gauge pressure P1 of the water in the pipe is 1.5 atmospheres. A short segment of the pipe is constricted to a smaller diameter of 2.4 centimeters. What is the gauge pressure of the water flowing through the constricted segment? Atmospheric pressure is 1.013 times 10 to the fifth power pascals. The density of water is 1,000 kilograms per meter cubed. The viscosity of the water is negligible. Answer in units of pascals. Okay, this one looks complicated a little bit, but first let's define what they mean by constricted, right? So this over here, constricted. I think it's somewhat obvious, but if you don't see it, it's okay. So what that means is here, exactly at this point, guys, the diameter is less, right? It decreases in diameter. And of course, we know it has to do with the cross section of what's going to affect the cross sectional area. So we're going to consider this cross sectional area over here, and then this one. Okay, we have both of them. We have two different pressures at two different sections, and we can use Bernoulli's equation, which is the one we have over here, right? Maybe you can see which is the one we're going to use now, because we don't have to use this whole thing, right? We don't have to. We'll write it down, and I'll show you how we can simplify it. Okay, so let us start with the given. Well, let me highlight the what we need to find. We need to find the gauge pressure and then I guess just this whole thing, right? Flowing through the constricted segment. That is what we need to find. Okay. Let us start with the given. Hopefully you can see that the pressure here will be lower than 1.5, right? Because you have a higher speed. We learned that higher speed is lower pressure based on the cross-sectional area. So let us write down our given. Given. We know velocity 1. This is the first velocity, right? We're going to call this one velocity 1. So velocity 1 is equal to 5.7 meters per second. And then we have this diameter for area cross-sectional area 1. So we're going to call this diameter 1, which is 3.4 centimeters. And I think we should label the stuff over here. So this is velocity 1. This one is cross-sectional area 1. This one will be cross-sectional area 2. We have velocity 2 over here, and then we have the pressures. Okay. And then we have the gauge pressure P1, so pressure 1 will be 1.5 ATMs, atmospheres. Come on, number 5, you can do this. And we have a second diameter of the constricted area, which is 2.4 centimeters. And we need to find gauge pressure, or P2 over here. Question mark. Okay. And that's all we have. Well, we know that the acceleration due to gravity is 9.8 meters per second squared. I meant to give you a conversion factor but I just left it as atmospheric pressure is 1.013 times 10 to the fifth pascals. So I'm just going to give you that one right now. So 1 atm, 1 atmosphere, is equal to 1.013 times 10 to the fifth pascals. So that doesn't affect my math right now. I'm just going to move this to the left side, keep it there. We'll use it when we have to use it, okay? There you go. You'll see why we need this one. It is very important. We know the density of the water. This is water flowing through the entire pipe, so it's not changing. It's non-viscous, incompressible. So density equals 1,000 kilograms per meter cube. There you go. That is all we know. Okay. And I'm going to copy Bernoulli's equation. Okay. There you go. She's blue. Uh-oh. No. Sorry. Let's try one more time. Let's change to blue. There you go. That's what I wanted to do. Okay. This is Bernoulli's equation. We have to use it. Okay. Let me add a horizontal line, because why not? Okay, let's talk about, we have different velocities. Yeah, that's true. Let's talk about the height. Well, if we take this point and this point, well, guess what? You have equal heights, right? The pipe is not changing height. Based on that, uh-oh, I don't know what I did, but based on that, we can say that height 1 equals height 2. And that is the case over here. Oh man, I forgot to write it down, right? So height 1 equals height number 2. And we can use this version of Bernoulli's equation, right? So the heights are the same. So we'll say equal heights, or H1 equals H2. Thus, pressure 1 plus rho g, oh no, that one cancels, plus the kinetic energy of the fluid, 1/2 rho v1 squared is equal to pressure 2 plus 1/2 rho v2 squared. Okay, here's the problem. We don't have velocity 2. So we need to find velocity 2. How can we find velocity 2? Well, we know that the flow rate is constant, right, on this pipe. And we know the continuity equation, which is area, well, cross-section area 1 times velocity 1 equals cross-section area 2 times velocity 2. So based on this formula, we can find velocity 2. So I'm going to divide by cross-section cross-sectional area 2 on both sides. And then to find velocity 2, I have cross-sectional area 1 times velocity 1 divided by cross-sectional area 2. How do I find my area? Well, the cross-sectional area is a circle, both cases. And I know the area of the circle is pi r squared. So area, in this case cross-sectional area, will be pi, that's an ugly pi, r squared. So then my equation will read, let's change this to green so it looks like we're doing other stuff. So then we have velocity 2 is equal to pi r1 squared times velocity 1 divided by pi r2 squared, and that's it. Notice how we can cancel pi, and we can find velocity 2 with this formula, well, equation. Radius 1 squared times velocity 1 divided by radius 2 squared. How to find the radius? Well, we have the diameter. Don't forget we have to convert this into meters, so we divide by 100. So radius 1 will be diameter 1 divided by 2. So radius 1 equals, it'll be 1.7 centimeters. So that'll be equal to 0.017 meters. Radius 2 will be 2.4 centimeters divided by 2. That is 1.2 centimeters. We divide by 100. 0.012 meters. Okay, so our velocity 2 can be found by multiplying 0.017 meters squared times velocity 1, which is 5.7 meters per second, and we're going to divide by 0.012 meters squared. If you want to argue with me that we didn't have to convert it to centimeters, this is just good practice. So you remember the SI units for distance are meters. Okay? So let's check it out. Uh-oh. Oops. Menu. And I'm going to move this one over here. And we have 0.017 squared times 5.7. I need to add another parentheses. You know how much I love parentheses. And then divided by 0.012 squared. Should be my velocity. It is about 11.4, right? We are using how many significant digits? 2, so, well, 11.4. We're going to use 11.4. Although I'm going to keep this number and I'm going to use it. We're going to say velocity 2 is 11.4 meters per second. And that makes sense because we said, well, we have a smaller cross-sectional area, so it has to go faster. Okay, we have velocity 2. Velocity 2 is equal to 11.4 meters per second. Now we can use Bernoulli's equation, the simplified version for equal heights. We'll have pressure 1 plus the kinetic energy, that is half rho V1 squared, is equal to pressure 2 plus 1/2 rho V2 squared. Okay, we're solving for pressure 2, so all we do is subtract 1/2 rho V2 squared on both sides. This cancels over here, and then my pressure 2 will be equal to pressure 1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared. I'm going to factor out the 1/2 rho because why not? So I'm going to have pressure 2 is equal to pressure 1 plus 1/2 rho parentheses V1 squared minus V2 squared. Before we use our number, before we substitute, we were asked to find this in units of pascals, okay? Our pressure 1 is in ATM. We have to convert our 1.5 ATMs to pascals. If 1 ATM equals 1.013 times 10 to the 5th pascals, and we have 1.5 ATMs, all we do is multiply 1.5 times 1.013 times 10 to the 5th pascals. Okay, I'm going to do that here. I guess we can call this the miscellaneous section. So we'll have we have 1.5 ATM, and then we know that 1.013 times 10 to the 5th pascals is the amount of pascals in 1 ATM. If you think about it, I'm using dimensional analysis, so normally we do this thing, right? And then I would have that, and I say, yeah, so we need to cancel ATM with ATM, so I'm doing the same thing. I just decided to do it this way. Okay, so this is pressure 1 in pascals. So let's try it. Keep clicking the wrong one, guys. So 1.5 times parentheses 1.013 e function, because that's times 10 to some power to the 5th power, close parentheses, divided by 1. So I have that'll be 151,950 pascals. So pressure 1 in pascals would be 151,950 pascals. There you go. Now I can substitute numbers. Okay, so pressure 2 equals pressure 1, 151,950 pascals. Let me fix this real quick. There you go. Plus 1/2 times the density, which is 1,000 kilograms per meter cube. It is the density of water. Times, use brackets, velocity 1 squared. That'll be 5.7 meters per second squared minus 11.4 meters per second squared. And that will cancel. And I'm going to end up with pascals. Okay? All right. So let's do this. I guess. Let's see. Ah, that's fine. I know what the number is. Okay. So we have 151,950 plus parentheses 1/2 times density, which is 1,000, times parentheses double 5.7 close parentheses squared minus parentheses, I'm going to use this number, 11.4396 close parentheses squared. And there you go. We have 102,763 pascals. Okay. So pressure 2 be 103,000? Oh, 2,763 pascals. Now, if you think about it, it makes sense because we have a higher pressure, lower pressure. So the pressure, it is lower than 151,000 or almost 152,000. So there you go. This is the answer.